Welcome back to EGME-333. This video will focus on the pressure variation on a fluid that is at rest. Now let's consider a fluid that is at rest. Physically, this indicates that the acceleration is equal to 0, and consequently, the basic equation of motion for a fluid reduces to the hydrostatic equation, which is given to us by the gradient of pressure plus the specific weight gamma in the z direction is equal to 0. So if we look at this equation term by term, we can interpret the gradient of pressure as representative of the net pressure force per unit volume at a point. And the second term, gamma times the k vector, is representative of the body force per unit volume at a point. The sum of these two forces per unit volume must equal to 0. Note, this equation is written in vector form. If we write it in component form, we can express it as the rate of change of pressure with respect to x, partial p partial x, is equal to 0. Then that the rate of change of pressure with respect to the y direction, partial p partial y, is also equal to 0. And that the rate of change of pressure with respect to z is equal to the specific weight gamma times a negative sign. Recall that the specific weight gamma is equal to the product of the density of the fluid ρ times the gravitational acceleration g. From looking at these equations, we can see that the pressure P does not depend on either the x direction nor the y direction. It is strictly a function of z. So the pressure P only depends on the z direction. Therefore, P is a function of z, and we can omit the first two equations and simply state that the rate of change of pressure, now a single variable function, dp dz, is equal to negative of the specific weight of the fluid, gamma. So if we apply the incompressible fluid assumption to the previously discussed hydrostatic equation, dp dc is equal to negative gamma, we can obtain an algebraic expression if we integrate the hydrostatic equation between 2 points, point 1 and point 2. So essentially, if we integrate the left side, we get the integral from pressure P sub 1 to pressure P sub 2 of dp. That is equal to negative gamma of the integral of from z sub 1 to z sub 2 of dz. I'll highlight here that the gamma has been factored out of the integral because gamma, again, simply depending on the product of the density ρ and the gravity g, is a constant. So to visualize z1, z2, and the corresponding p1 and p2, we can say that z1 would be some vertical position z sub 1 with its corresponding pressure p sub 1, and z sub 2 would be some position with its corresponding pressure p sub 2. So if we integrate, what we end up with is that p sub 2 minus p sub 1 is simply equal to negative gamma z sub 2 minus z sub 1. I can multiply both sides by negative 1, and that leads to p sub 1 minus p sub 2 is equal to gamma times z2 minus z1. Essentially just got rid of the negative sign on the right-hand side and flipped the two terms on the left-hand side. Now, if I specify the value h as the difference between z sub 2 minus z sub 1, then I can simplify this expression as P sub 1 minus P sub 2 is simply equal to gamma times H, where H is the depth of point 1 relative to point 2. Conceptually, we can interpret it as that in an incompressible fluid at rest, the pressure varies linearly with depth. Essentially, the pressure must increase with an increasing depth in order to hold up the fluid above it.